Okay, now we're going to work on some buffer problems. Okay, and we're going to, the first thing you need to be able to do is identify reactions that create buffers. So remember, buffers are made of an acid and its conjugate base, weak acids, weak bases, together in solution. Then, whenever you're presented with a buffer problem, you're probably going to use the Henderson-Hasselbalch equation. And just to remind you what this looks like, we have the equation written here. It's pH equals the pKa plus the log of the concentration of the conjugate base over the concentration of the acid. Okay, so what this really means is that we have our titration curve, and it will look something like this. And the midpoint is the point at which the concentration of A minus equals the concentration of HA. So we have equal amounts of protonated form and deprotonated form. And when that happens, these two numbers will cancel. The log of 1 is 0. So at this point, the pH equals the pKa. Okay, so that's a very special point that you should keep in mind. This is the midpoint. Okay. So let's get into actually working some problems. So calculate the pH of a solution that results following the addition of 10 mils, so we're given a volume, of 1 molar, here's a concentration, of a base, to 40 mils of 1 molar NH4Cl, or NH4Cl, so ammonium chloride. So what we're doing here is we've got 10 mils of sodium hydroxide plus 40 mils of NH4 plus, simplify that, and so we're making a final solution of 50 mils sodium hydroxide plus ammonium chloride product. Okay, so where'd I get the 50? It's because it's 10 mils here, 40 mils here. When you combine them, makes 50 mils. Okay, so we're changing the volume of each of these solutions. So we start off with 1 molar concentrations of each. Alright, so 1 molar, at 10 mils of 1 molar means that we can calculate the number of moles as 0.010 moles of NaOH are added to 0.040 moles of ammonium chloride, and then we have a 50 mil solution resulting. So let's draw out what this would look like. So let's do the general equation first before I get ahead of myself. So we have an acid, we have a base. We're going to combine the acid and the base to make water, and we'll be left with the conjugate base here. Okay. So our acid in this case is going to be NH4 plus, and that is going to relate to the conjugate base by losing one of those protons, NH3. Okay, and then the base, sodium hydroxide, is going to become water. So this is the base and its conjugate acid. Okay, so this is going to go partially forward, partially backwards because we're combining things, etc. So now we can make our ice chart, and we've already identified what's the acid and what's the conjugate base that we're going to be looking at. HA is here, A minus is here. Okay, initially, so we could do this in terms of concentrations, but it doesn't matter if you do concentrations or moles. So I'm just going to do this in terms of moles. As long as all your units are the same, then it's fine. So we're starting out with 0.040 moles of ammonium chloride. It's very important that you don't use the volumes. Volumes don't tell you anything. We only care about moles and molarity in the ice charts. Sodium hydroxide, we're starting with 0.010 moles, and we initially start with nothing, and actually water doesn't have concentrations, and we start with no ammonia. Okay, So, how do we know how much is changing in this reaction? Well, this is going to consume some of this proton and become water. How much of what is going to react? You look at the lowest number, and 100% of that is going to react. So this is our limiting reagent. It has the lowest number of moles. So 100% of this is going to be converted into product. And so we can't react any more moles. 100% of this is going to react with the same number of moles here, and we're going to gain the same number of moles over here. Just like when we were using X's in the weak acid problems. We're losing and gaining the same amounts. So it gives us an equilibrium value of 0.30 moles of HA, no moles of OH minus, water doesn't have concentration, and 0.010 moles of A minus. So now we have different molar ratios of A minus and HA, so what we need to do now is, and we have to solve for pH, so now we're going to use Henderson-Hasselbalch. So in order to use Henderson-Hasselbalch, this equation, we're going to have to look up the value of pKa for ammonium chloride. Plus, because we know the concentration of A minus, we know the concentration of HA, and we're looking for the pH. So we don't know, we have to look this up, we know this, we know this. Okay, so when we look up the pKa, we see that it is 9.25. So now we just have to take the ratio of these two, and remember this is concentration, and concentration has to be in moles per liter for the top and the bottom here. So I'm going to do the moles in pink. 0.010 moles of the A minus here. And what's the total volume? The total volume is that 50 mils, which is 0.050 liters. Okay? So that's the concentration of A minus. Okay. And now we're going to do the same thing for the concentration of HA. So HA, number of moles of HA is 0.030 moles, and the total volume again is not going to change. We took 10 mils plus 40 mils, we ended up with 50 mils. 50 or 0.050 liters. And what you will notice, to make your life easier, these cancel. Moles cancel. So you end up with 9.25 plus the log 0.010 over 0.030, and after you do that and figure out the logs of, so in step 1 divide this, step 2 plug it into the log, you get 9.25 minus 0.602, which gives us a final pH of 8.85. Remember, take the significant digits of the number with the fewest significant digits. This is tenths hundredths place, this is tenths hundredths thousandths place, so we go to the hundredths place. And this is what the pH is. So you do this when you have ratios of HA and A minus to figure out what the pH would be. Okay. Next question. Little more challenging. Suppose you want to make a buffer of exactly pH 7. So we're given that pH is going to be 7.00. Notice the significant figures. Using KH2PO4, so this is a phosphate buffer, and Na2HPO4. So this is potassium phosphate, this is sodium phosphate. And the final solution is 0.1 molar for KH2PO4, what concentration of the sodium phosphate would we need? So what concentration is what we're looking for. And so we know that this is a buffer problem because it uses the word buffer in it, so we know that we need to start off with Henderson-Hasselbalch, which is pH equals pKa plus the log of the concentration of A minus over concentration of HA. So we're given one concentration and we need to find the other. So which one is which? HA or A minus? The one with more H's, the one with two H's, is HA. The one with fewer H's is A minus. So this is the acid and its conjugate base. When in doubt, follow the protons, because the one definition of an acid is a proton donor, the other, and then the base is the proton acceptor. That's perfectly valid. More protons, more acid. Okay, so we know concentration of HA is 0.1 molar. The final solution, so this means it's already at equilibrium. We don't have to do an ice chart. Hooray! But we need to find the concentration of A minus. Okay, so we have to look up the pKa because it's the last piece of information. This is always a given unless you're trying to solve for it. But generally, this will be given to you, or you look it up. And the pKa here is 6.86 for this phosphate buffer that we are making. So now we just plug and chug. 7.00 equals 6.86 plus the log of concentration of A minus, we have no idea what that is, over concentration of HA is 0.1 molar. Okay, so now subtract 6.86 from both sides, and we get 0.14 equals the log concentration of A minus over 0.1 molar. Hold up. Okay. So now, how do we get rid of this log? Because this is the log of this entire expression. We can't, how do we get rid of this? Remember, log is base 10. So, if we take 10 to this power and 10 to this power, this 10 will cancel out the log. And when we take 10 to the 0.14 power, we get 1.38. And when we cancel out this log, we get concentration of A minus over 0.1 molar. Okay, now we just simply multiply both sides by 0.1 and we get concentration of A minus equals 0.138 molar. And that is the answer. So obviously we can take the Henderson-Hasselbalch equation and solve for concentrations, we could solve for pKa, or we could solve for pH. So I'm not going to show you every single possible question, that would be impossible, but just keep in mind that this is a very powerful tool as long as you remember to use 10 to the power of something to get rid of the log when you're algebraically solving these questions.